imagined a concrete so strong you could mold it into these impossibly thin, elegant structures? And so durable it could last for centuries with almost no maintenance? Well, today we're diving deep into the future of building, ultra-high performance concrete, or UHP. And trust me, this isn't just an improvement, it's a complete reinvention of one of the world's most common material.
So I want you to just think for a second about the sidewalks, the buildings, the bridges that are all around us. Now, what if the material they're made of could be, and I mean this literally, 10 times stronger? It honestly sounds like something out of science fiction, but it's the reality of UHPC. The benchmark for this new class of material is a compressive strength greater than 150 megapascals. Now, to put that into perspective for you, that's like stacking 3 full-size elephants on an area the size of a postage stamp. This isn't just a small step up, it's a quantum leap that unlocks entirely new possibilities in engineering and architecture. Okay, so to understand why this is such a massive deal, we first have to look at the hidden flaws in the concrete we see every single day. You know, its tendency to crack and degrade over time. That's something we've kind of just accepted, well, until now. You see, for all its strengths, the concrete we're all used to has a pretty big Achilles heel. It's porous, which means water and nasty chemicals can seep right in, causing it to break down over time. And it's brittle. It cracks and fails without giving you much warning. These limitations are exactly what UHPC was designed to overcome. So what exactly is UHPC? Well, it's a revolutionary cement-based composite, and the keywords here are engineered and composite. It's engineered for absolutely exceptional strength, ductility, and for ductility, think of it like a metal paperclip that bends and deforms before it snaps, instead of a dry twig that just breaks instantly, and a service life that can easily exceed a century. And according to researchers like Manoj Balakrishnan, UHP really represents a fundamental shift in thinking. As you can kind of see from this mind map, it's all about engineering a material from the microscopic level all the way up. We're talking about addressing everything from its composition and performance to its durability and how it's used. So how in the world do you create a super material like this? Well, it all comes down to a very specific and highly optimized recipe that fundamentally redesigns the entire concrete matrix. All right, so what's the secret sauce? On the screen, we see some familiar ingredients, you know, Portland cement and sand. But the real magic is in the details. We're talking about ultra-fine silica fume that fills in all the microscopic voids, super plasticizers that let us use way less water, and these tiny still fibers woven all throughout the mix. The crucial point here is achieving what engineers call optimized particle packing. Think about it like filling a jar. You start with big rocks, then you add pebbles to fill the gaps, then sand, and finally water. UHPC does the exact same thing, but on a micro level, with different sized particles, creating an incredibly dense and non-porous material. And this quote from Manoj Balakrishnan just hits the nail on the head. This isn't about just tweaking a recipe through trial and error. No, it's a major shift to a scientifically optimized system where every single ingredient is chosen to do a specific job in creating a near-perfect material. So, after all that meticulous engineering, what are the results? Well, the performance characteristics are, frankly, astounding. This side-by-side comparison really says it all. Where conventional concrete is brittle, UHP is ductile. Where one is porous and vulnerable to the elements, the other is dense and practically impermeable. This lets us create thin, lightweight structures that last not 50, but over 100 years with minimal maintenance. So what's the secret to that amazing ductility? It's those steel fibers we saw in the recipe. They act like a 3-dimensional web of microscopic rebar inside the concrete, holding everything together even after the first tiny cracks appear. This is what prevents a sudden, catastrophic failure and lets the material absorb a huge amount of energy. Okay, so we have this incredible material. What does it actually mean for the world around us? It means we can start building a stronger, more resilient, and believe it or not, a lighter future. First up, let's talk bridges. Because UHPs is so much stronger and lighter, we can design bridge girders that are way thinner and can span much longer distances with fewer supports. This doesn't just change how bridges look, it also speeds up construction like you wouldn't believe. And in skyscrapers, we can use UHPC for facade panels that are incredibly thin yet super durable. This reduces the building's total weight, what we call its dead load, which means we can have smaller foundations and more efficient designs, really letting architects push the boundaries of what's possible. And, maybe the most important thing of all is that we can build infrastructure that's actually designed to last for over a century. Its incredible resistance to water, salt, and freeze-thaw cycles means way less maintenance, lower life cycle costs, and just greater resilience for our critical public works. And the applications are just so versatile. We're seeing it pop up everywhere, in these sleek bridge decks and elegant architectural panels, in structures designed to withstand earthquakes and blasts, and even in super thin overlays that can breathe new life into our aging infrastructure. Now, UHP is a total game changer, but it's not without its challenges. It's really important to have a balanced perspective on where the technology is today and, of course, where it's headed. So the three main hurdles right now are cost, complexity, and access. The specialized ingredients, like those steel fibers and silica fume, they make the initial material cost higher. It also requires specialized equipment for mixing, and in a lot of cases, the formulas are proprietary, meaning they're owned by specific companies. But the good news is the global research community is actively tackling these issues. The big focus right now is on developing open-source, non-proprietary mixes and finding more sustainable ingredients. The goal is to make UHP much more affordable and accessible for everybody. Which leaves us with a final thought. Our world faces these immense challenges that demand stronger, longer-lasting, and more efficient infrastructure. So the question we're left with is this: is this incredible material, UHPC, the very foundation that we will build the next century upon?